Okay, in the last lecture, we covered section, let's see, 2.4. This section was called the precise definition of a limit. And in that video, we basically took all of these intuitive ideas of what a limit should be, and we made it mathematically precise. We stated a very precise definition, this epsilon delta definition, which was supposed to capture all the ideas that we had developed in the previous sections when we looked at, for example, um, how to make sense of the notion of instantaneous rate of change or instantaneous velocity. It was based on this idea of a limit. And so in that section, we made the idea of a limit precise using this epsilon delta formulation. But we saw that the definition could be pretty cumbersome. Um, So let me just remind you what that definition looks like. So let me share my screen. So what you have is we saw that this a limit as x goes to a, f of x equals L means the following. So this is a state, this equation has a lot of meaning. It's full of a lot of meaning. And what it means is the following, that for every epsilon, some small positive distance, there exists, or you can find another small positive distance delta, such that if the distance from x to a is less than delta, then this implies that the distance from f of x to L is less than epsilon. So if I give you some small distance, and I want f of x to be within that distance to L, you can always find a small distance delta, such that when x is that close to a, that will ensure that f of x is that close to L within epsilon units. And we proved a couple limits, but as we saw, it was kind of cumbersome. And it involved a lot of work just to prove one result. There was a lot of work that went to just proving one example. So, and as I hinted at in the last video, that really is motivation to want to develop more theory surrounding these limits. So we want to develop more theory so that we can have some tools and techniques at our disposal that can handle a wide range of problems and examples. And that's literally how all of mathematics proceeds, is about you start with some basic ideas that start with a concrete problem. You try to abstract the essential details of the problem and then formulate these ideas mathematically. And then from there, this will be like your foundation of your theory. You draw consequences of those ideas. And so that's what we want to do in this section. So, and just to give you an idea how complicated this epsilon delta definition can be, let's say, for example, we want to show that. So here's an example of how complicated this definition can be, and reason for looking at reason for developing theory around these limits. So, for example, and we will look at this example later on, actually, you could have something like the following. You have that you want to take this limit of this fraction here, um, as, sorry, that's 3x. So the limit of this fraction as x goes to -2, and it's allegedly negative 1 over 11. And first of all, this is hard in itself to determine. How do you determine? It's like, suppose I don't give you that it's equal to negative 1 over 11. I just ask you, what is this limit? Does it exist? What is the value? That's a hard question itself. So first of all, I'm giving you half of the problem. I'm giving you more, actually more than, yeah, I'm giving you half of the problem. I'm telling you what the limit is and that it exists. So that's another hard aspect of this problem that I'm just sweeping under the rug. But also, if I give you this and I ask you to prove this, prove using the epsilon delta definition, what would that look like? Let's not actually go through it, but let's just set up the definition and see what it would look like. Well, it would say that for every, the first part would be the same, for every epsilon greater than zero, there exists a delta greater than zero such that, ST just means such that, if I haven't explained that already, x minus minus 2 less than delta implies that this fraction right here, x cubed plus 2x minus 1 over 5 minus 3x, and then minus 1 over 11, absolute value is less than epsilon. So I would give you this is how you would go about justifying this equation right here that is proving that this equation is true using the epsilon delta definition. I would hand you an epsilon, just some general epsilon, and then you would need to find a delta such that and of course this delta is going to be defined somehow in terms of the epsilon. We saw that a lot in the example that delta could just be taken to be just equal to epsilon, or sometimes maybe delta was the square root of epsilon, or maybe it was epsilon squared, or maybe epsilon over 3, some sort of a delta would somehow be defined in terms of epsilon. But I would give you this epsilon, you would have to find the delta that makes this implication work. That is, if this holds, if this is true, this first statement, then this will be true. And you can imagine that's a lot of busy work, trying to figure out how that would, it could be really complicated. And honestly, I don't even know exactly myself how I would do that. And maybe I would combine these fractions here and just kind of play around with the arithmetic and then try to make a guess as to what delta would be. So you can imagine that this is a really complicated problem. And this is just, that would be a lot of work to just solve one problem, this one example. So what we want to do, as I said, is to figure out to prove some general results that'll enable us to solve a wide variety of problems. All right, so let me I want to share the book because there's uh, a lot of information from it that I think is helpful. So as I said, we're in 2.3, calculating limits using the laws. We did things a little backwards. I don't like jumping into 2.3 first. I like to do 2.4. Um, because we're going to actually prove some of these. We're going to prove some of these laws, right? We're probably just going to prove maybe just number one. So it turns out we have a lot of nice laws. When we get to talk about continuous functions, which will be in the next video, these laws are going to be extremely helpful because, for example, using these laws, we're going to be able to prove that all polynomials are continuous, and that's going to greatly simplify many limit calculations. So what does this say? Well, it says you have some constant c. This is the number that you're going to approach. And then you're assuming you have this constant, sorry, pen didn't work. You have this constant c, and then you have to assume that these limits exist. So not really a whole lot you have to assume. Usually you're given limits that do exist. And c, as I said, is the number that you're oh, this is a typo in the book, actually. Look at that. Oh, it's not. Okay, C does end up appearing. They don't even talk about A. Really, this is like incomplete statement. I thought C was going to be the number your approach. C is just ends up being this constant multiple right here. Um, so um, really, you should have talked about A being some other number as well. This is an incomplete statement. But anyway, so A is this number you're going to approach. And so this first one says that when you take the limit, assuming that these individual limits exist, if you want to take the limit of the sum of these functions, um, then you can just take the limit of the individual limits. Same thing for the difference. You can take the difference of the limits. The third one is that if you take a multiple of a function, a scalar multiple, you can, in a sense, factor out the scalar c. This one's really easy to prove, actually. This is probably the easiest one to prove of all. Maybe I'll prove that one as well. That one's not hard to prove, 3. And 4 is maybe a little trickier. I can't see that in my head. This just says that if you take a limit of a product of functions, then it's the product of the limit. So you take this is a limit of the product, it becomes a product of the limits. And then you have the same thing for quotients. If you take the limit of a quotient, it's the quotient of the limits. The limit, in a sense, distributes over the numerator and the denominator. But you just have to stipulate this, of course, because you don't want division by 0. So 1 and 2 can actually kind of be combined. Sorry, 1 and 3. Basically, it can be combined as follows. So it says that if you take the limit of c times f of x plus g of x, it's going to be equal to c times the limit as x goes to a, f of x plus the limit as x goes to a of g of x. 2 is kind of redundant. This 2 follows from 1 and 3. But 1 and 3 together, they tell us, now this is just for your edification. It's not going to be something that you need to know for this class, but just like if you're interested in math and you want to know what's coming ahead, it turns out that 1 and 2 can be, there's a nice concise way of stating this. What this tells you is that the limit operator, the limit is what's so-called is a linear operator on the infinite dimensional. Oh, sorry, I didn't finish this. Is a linear operator on the infinite dimensional space of functions. So in another video, I talked about how mathematicians like to think about space and different spaces. We're just going to mostly think about the real line, but it turns out you can look at all the functions from the real line to itself, and this itself will be a space. It'll be a space of functions on the real line, or more generally, just any set. And then this says that that if you look at this infinite dimensional space of functions, then the limit this limit thing right here is itself a function. It's actually a linear operator because it distributes over stubs in this way, and you can factor out scalar multiples in that way according to 3. So 1 and 3 together say that the limit is a linear operator. All right, so now how does this help us? Well, this is a kind of a dumb example. Let's go to the other example. Oh, actually, okay. So here's some very quick consequences of the limit laws that I just showed you. So you have this power law. The power law is actually easily follows from the multiplication law. So if you have f of x to the nth power, what does that mean? It means that you're taking f of x times itself n times. So f of x times f of x times f of x. And now now we know that if you have a limit of a product of two things, it's the product of the limits. But that obviously easily generalizes to any finite product, right? So this limit right here, so let me just carry it over here, is going to be equal to the limit as x goes to a of f of x. So the limit is going to distribute over the product of n, these n terms. They're going to be n terms here. And then limit time of as x goes to a of f of x times the limit as x goes to a of f of x. And then this has n terms, and they're all the same. So you have the limit, this will end up just being the limit as x goes to a of f of x, and that it'll be the whole thing to the nth power. So in other words, like you can take the, if you have something to, you take the limit of something to the nth power, you can take the power out and just, you can do the limit first and then take the nth power. So it like kind of, in a sense, factors out, I guess. I don't know if that's the right terminology. Um, and you can do the same thing for roots. There's this case, so the root law, so we just did the power law, there's the root law. And you can do the same thing for roots. I won't go through it. Maybe if you want for your own sake, you can. But you just have to, for when the n is even, you have to be careful because you need to assume that the limit is positive. Because if it's not, then you're taking this, let's say you're taking the square root of a negative number, and that wouldn't work. And then there's these special limits right here. These are kind of basically true. These are like trivially true. Like, so, like, first of all, let's think about nine. Why is that? I mean, you technically have to justify everything by the epsilon delta definition, but it's almost, there's nothing really to prove almost. When you write down the definition, you'll see there's not really anything to prove. In this case, if you write down the epsilon delta definition, you're just going to take epsilon to be delta. That's it. And I think the same thing over here. You can just take epsilon to be delta to prove that. But just without writing that down, what does this say? It says when you want to take the limit of x as x approaches a. So you're asking, what does x approach when x approaches a? Well, it just approaches a, right? That's just going to be true by definition. This one maybe is not as obvious, but basically thinking about it in terms like geometrically. If you have a constant, that's like a vertical line, right? Or horizontal line, right? So we're talking about a constant c. So this is like a line y is equal to c, and then say a is right here, and you want to take the limit. So you got to consider points to the left of a approaching a, points to the right of a approaching a, and then you got to like look at the height, the corresponding height. But you can see it's just it's a constant function that every point is at the same height. So it's going to just approach c. So the limit of a constant is just the constant itself. And then we get this. This is an easy consequence. I mean, this is just follows from the power law, right? Yes, as if we put f of x equal to x in law 6 and then use law 9. So you're gonna use the power law and then this law. You can see that that is 10 is a consequence of 6 and 9. So that's a consequence, a very easy consequence. It's actually be extremely helpful though, especially when we talk about continuous functions. All right, let's see. So here's the example we actually just looked at. Um, so we'll get to that in a moment, but let's look at A first. So again, you could technically write down the epsilon definition, epsilon delta definition, and you could determine this limit first, and then you could prove, so they determined that the limit is 39, so this is 39. And assuming you already knew this was 39, which is not easy to know in itself, you could justify this right here using the epsilon delta definition. But it's going to be cumbersome. It's going to involve a lot of details, and it's going to be a lot of time to just solve one problem. So let's use all our laws. So here's a breakdown of problem A using all the laws. We didn't prove all of them. Um, we didn't prove any of them actually yet. I will prove one of them at the end though. But we're just going to take them for granted for now. We're going to assume that they're true, and I will justify one of them at least, or two of them. So we have this limit, and we know we have a sum of things, right? So this is, we can distribute the limit over the sum of each term, right? So this is law 2 and 1. So let me scroll up and remind you what 2 and 1 are. So 2 and 1, okay, so 2 is about the differences, a limit of a difference, and 1 is about a limit of a sum. And then we're going to also use this law too, as well. Number 3, where you have a constant multiple and you can factor it out. So first of all, we use we go from here to here, we use we distribute the limit over sum and the difference. Here's a difference, there's a sum. And now we can use the law, the scalar multiple law, and we have this 2, we have this 3. We can factor those out to get 2 times the limit, 3 times the limit. And now finally we can use 10, right? Well, let's see, what do they use? Oh yeah, well, they use the constant law. So this is just the limit of a constant, so it's going to be 4. This is just the limit of x, so if x approaches 5, x approaches 5. So that's why you just write 5 down. Of course, you have this 3 times the 5, and then you have x squared. So if x approaches 5, x squared is going to approach 5 squared. And then you just do the arithmetic and get that. All right, so now let's see. So now because so we have the limit of this fraction here. Whoops. And the limit of this fraction here. And because if you take the limit as x goes to -2 of 5 minus 3x, this is not going to be 0, right? In fact, it's going to be when you go through all these calculations, it's going to be 11. So because it's not 0, we can use that quotient limit law. So you take the limit of the fraction, you get the fraction of the limits. So there's a limit in the numerator and limit in the denominator. And at this point, you can distribute the limit over each piece using the sum and difference law. So we have a sum here and we have a difference here. So now we can distribute in that way, and then we have x cubed. So that means when we take the limit of x cubed, we get -2 cubed. So we get that piece here. And then we have a scalar multiple. So we pull the scalar multiple out. And then we so now we have 2 times -2 squared, because we're taking the limit of x squared as x approaches -2 here. And then finally we have minus this limit right here, but this is just a constant, so it's just gonna be, and the constant is 1, so it's gonna be -1 right there. And if you go through the arithmetic, you simplify this, you get -1 over 11. So it turns out that we have this, this is actually continuity. We're going to see that this right here, we have this direct substitution property. If x is a polynomial or a rational function and a is in the domain of f, then you can just take, if you want to compute this limit, it's the same exact thing as just plugging the number in itself. And we sort of saw that in a couple different examples, especially the last video. So let's prove this one right here. This one's actually not that bad to prove once you have all the limit laws. So let's proof of direct substitution. Substitution property. So we're just going to assume that we have a rational function, and it will imply that the direct substitution property holds for polynomials, because every polynomial is a rational function. So we're going to say we have we have f of x is equal to p of x over q of x, and p of x and q of x are polynomials. So this implies that p of x is, say, an xn, an minus 1, xn minus 1, etc., to a1x plus a0, and and then let's see, q of x is going to be bm xn plus bm minus 1 xm minus 1, and then some intermediate terms, b1x, and then plus b0. M and n, maybe they're the same, they don't have to be though. And so now so we're told that a is in the domain of f. So that implies that Q of X, actually now I'm thinking, you think you need to do polynomials first, actually. So let's actually just prove this for polynomials. I think you need, now that I'm going through the steps, I think you actually need uh prove this for polynomials first and then prove it for rational functions. That's kind of interesting. I didn't expect that. So let me erase that. So it'll be clear how to prove it for rational functions though. Because a rational function is just going to be um a fraction of polynomials. So let's just assume f itself is a polynomial. So it's going to be, say, bn xn plus bn minus 1 x to the n minus 1 plus some intermediate terms and then b1x and then b0. So we're going to take the limit as x goes to a of f of x, and we want to prove that this equals f of a. I want to prove that this equals f of a. So let's do that. So it's going to be the limit as x goes to a of, well, what is f of x? It's this polynomial up here. I wrote above. Whoops. And then some intermediate terms plus b1x plus b0. And now I can take, so I have a sum of a bunch of terms, right? And so I can take the limit of the sum. So it's going to be a limit as x goes to a of bn x to the n plus limit as x goes to the a. It's tedious, but it's not that hard to prove. B to the n minus 1, x to the n minus 1, plus some intermediate terms, plus the limit as x goes to a of b1x, and then finally the limit as x goes to a of this constant term b0. So now I can I have a b to the n, b to the n minus 1, b1, and b0 are constants. So I can factor those out. So I'll factor that out, and I'll get b to the n times the limit as x goes to a of x to the n plus bn minus 1 times the limit as x goes to a of x to the n minus 1 plus b plus some intermediate terms plus b1 times the limit as x goes to a of x, and then plus the limit as x goes to a of b0. Now I have x to some power, I have x to another power, and then I just keep going down. And we know that we can just plug in to evaluate this limit and this limit and this limit and even this one, really, in a sense. You just plug in a for the x. So we have b to the n, and this will be a to the n, plus b to the n minus 1, a to the n minus 1. And then plus your intermediate terms, and then b1a plus, now this is a limit of a constant, so it's just going to be the constant b0. But what is this right here? This is literally just evaluating the polynomial at a, right? So this is our polynomial right here. And if you plug in a, you get exactly what we had down there. B to the a, n to the a, plus b to the n minus 1, a to the n minus 1. Intermediate terms, b to the 1, a, plus b0. So this proves the result. We have that if you take the limit of f of x as x goes to a, and f of x is a polynomial, then it's the same thing as just evaluating the function at, if it's same thing as evaluating the polynomial at that point that you're taking the limit. So this is actually gonna, as I said, be the defining property of a continuous function. So polynomials are the nicest functions you can encounter. Even rational functions are very nice. And so these are like the basic building blocks in a sense for continuous functions, and that's going to be made more precise if you want to take Calc 2. You'll prove that actually every continuous function is in a sense an infinite polynomial. has infinitely many terms. It's a what you call a power series. So polynomials are very important functions. They're the building blocks for continuous functions, and they're like the paradigm of a continuous function. All right, so that proves that result. And then, as I said, I didn't do the rational part, but the rational part's easy. If, in that case, you take f to be, as I was doing before, p of x over q of x, where p and q are polynomials. And then when you take this limit right here, it'll just be a limit of the fraction. So you just distribute the limit operator over the numerator and the denominator, and you just do this exact calculation in the numerator and the denominator, and you get the result. So not that hard to prove. All right, so now um, let's look at a function. So we've kind of seen where this result works, right? So actually, maybe let's see, do we have? Let's go back to our one example. Where is it? Trying to find it. All right, so this is example two. Let's just go through the steps and see if we get the same result. So we have this rational function. We computed this limit, and we found that it was 1/(-1/11). So note, we want to compute this, and we can say note, the quotient is defined at x equals -2. It's in the domain of this quotient. So according to the direct substitution law, I can just literally plug in -2. Plus 2 to the -2 squared minus 1 over 5 times minus 3 times -2. And then this will be -8, and this will be 4. Oh wait, no, that's not right. Oh, this will be -8. Oh, +8, so -1 in the numerator, and then this will be 11. So that's exactly what we found. And this was a lot fewer steps. And that's because we have this other tool, this other technique, this direct substitution property at our disposal. So this is going to be a very common theme even throughout this whole course, but throughout mathematics more generally, is that you're going to start with some really basic ideas, draw some conclusions. So we're going to talk about continuous functions next, and we're going to draw a bunch of conclusions about continuous functions and properties of them. And then we're going to talk about differentiable functions. We're going to introduce the basic idea, and then we're going to talk about properties of differentiable functions and to draw some conclusions about them. All right, so that's a nice property to have at our disposal, but it turns out that this doesn't always work. So let's look at this example. But there are some other techniques that we can use to simplify things. So this is example 3, and we want to find the limit as x goes to 1 of x squared minus 1 over -1. Note, quotient in this case is not defined at x equals 1, right? If you plug in 1, you're going to get 0 in the denominator. So that's a problem. So we can't use the direct substitution. However, we can do a factorization. We can factor in the numerator as x minus 1 times x plus 1 and keep the denominator as that. And then we can cancel out the problematic part. So the problematic part was this x minus 1 in the denominator, which gave us this division by 0 and meant we couldn't just compute the limit. But we can now cancel out this x minus 1, and we get at the limit as of x goes to 1 of x plus 1. And now we can note, in this case, x plus 1 is defined at x equals 1. It's just a polynomial, right? It's like a very simple polynomial. So and now at this point, I can use direct substitution, plug it in, and get 2. So here's going to be a more general fact that maybe I don't know why they didn't actually write this down first. But this is a fact we used, and this is not hard to prove. Um, this just follows from the definition of a limit. You got everything, any limit law that I'm stating either follows from another limit law or has to be proven using the epsilon delta definition. So just want to let you know that. So we have this fact, and this one you're gonna have to use the epsilon delta definition to justify. So what this states is that you have these two functions and they agree that they're equal when x is not equal to a. Maybe they equal at x at a, who knows? But they agree everywhere else. They might just differ at this value a. If that's the case, then it turns out when you take this limit as x goes to a of f of x, you can just compute the limit as x goes to a of g of x. And that's exactly what we did in here. So up here, f of x was this quotient, and g of x was this function right here. So it turns out that um, x squared minus 1 over x minus 1 equals x plus 1 for x not equal to 1. So these two functions are actually the same when x is not equal to 1. So we can use this fact right here. And this fact is basically true because when you take a limit, you don't care about what's happening at x equals a. All you care about is what's happening close to it. And so if these two functions agree very close to a, but possibly not at a, then it should, morally speaking, be the case that their limits should be the same because these two functions look the same. Actually, they are the same, very close to x equals a, but possibly not x equals a. Um, let's see. So that's an example of that. Let's see what else. What other examples do we want to go for this? Um, all right. I guess I should go over this one. This one's a good example. So this is going to relate to derivatives actually. So this is example 5. We actually already saw this limit. This is this limit right here. The limit as h goes to 0. We saw something like this when we were talking about the velocity problem, the instantaneous velocity problem. We saw a limit that almost looked exactly like this. So this was like p of 3 plus h, and then this was just p of 3. And in this case, I guess p of x, or maybe p of t, it would be equal to t squared. So this is like, this is like your position as a function of time, and you're computing this limit here. So no, we can't just directly plug in. We can't use this is another example where we can't use the substitution law directly. Because if you plug in 0, you're gonna get 0 in the numerator. So sorry, 0 in the denominator, but you also get 0 in the numerator. These are called indeterminate forms, and that means that you can't determine what the limit is. You need to do some sort of manipulation, like we did in the last example. So we're going to do that first. We're going to FOIL. So we're going to get 9 plus 6h plus h squared, and then minus 9 over h. And look at this. This is going to work out nicely because we can cancel the 9s. And then we have a factor of h here, factor of h here, and then a factor of h in the denominator. So this is going to simplify to 6 plus h. And now, so we have that this thing equals this fraction near 0, but not at 0, of course. They don't agree at 0. This is not defined at 0, but this is. So we can just use the direct substitution law to get 6. All right, here's another example where we can't use the substitution law immediately. We have to do some sort of tricks. So this is almost kind of like the same example as above, but instead of talking about square roots, sorry, instead of talking about well, actually it's a little different. I'm not even I'll just leave it at that. It's similar, but not completely the same. So we want to compute this limit. If you try to plug in zero right away, you're going to get zero over zero, and that's bad. You get in the indeterminate form, an indeterminate form. So that means we need to do some sort of manipulation. And it turns out you need to use what's called this trick called rationalization. So in this case, we have a square root in the numerator, and we want to get rid of that. So what we do is we multiply by what's called the conjugate. So you're gonna multiply and divide. Remember, you can't just multiply a fraction by something. You have to multiply and divide, otherwise you're changing the fraction. So the conjugate is basically you take the thing in the numerator, the square root of this thing minus 3, and you just change the sign of the 3 to positive. Now, if I multiply that by that, I have to divide by that. That is, I need to multiply by 1 in a clever form. So this thing in the numerator is called the conjugate. It's the conjugate of this thing right here. These are conjugates. And you'll see that this is actually it's very helpful. It might look weird, like a weird thing to multiply by at first, but it's actually really helpful because when you multiply the numerator, you get t squared plus 9 minus 9 over t squared, and then in parentheses you get t squared plus 9 plus 3. And look what happens. In the numerator, the nines cancel, and then you have a t squared and a t squared. So that bad part cancels out. The part that didn't allow us to immediately use the direct substitution property, that part cancels out. What we get is this. And now you can just plug in. Oh, I made the square root sign too big. Now in this case, you can just use the direct substitution law. So what you're going to end up with is t squared plus 9 plus 3. And this thing right here is defined at 0. So just use the direct substitution law and plug in 0. Actually, we're not, now that I'm thinking about it, we're not actually using direct substitution law because this is not a rational function. No, not a rational function. It's not a ratio of two polynomials. But what we can use are all our limit laws that I presented at the beginning. Whoops, I'm going to pull it up right now, but we can use, whoa, did not mean to do that. We can use these right here. So I'm going to just kind of use them all, these ones and the this one right here, because we have a square root. So when you combine all those together, you get 1 over square root of limit as t goes to 0 of t squared plus 9 and then plus 3. The limit technically distributes over to the 3 as well, but 3 is a constant, so you don't need to when you take the limit of a constant, you just got the constant back. Now, here's where we're going to use the direct substitution law. T squared plus 9 is t squared plus 9 is a polynomial. So we can use the direct substitution method here. And what we get is the square root of 0 plus 9 plus 3, and then that'll give you 1 over 6. All right, so let's look at, let's see, what other examples? Got that. Okay. All right, before I go to, I want to jump ahead again to 2.4 because I want to prove two of the laws. So let me prove, because I think it's good to see how these definitions work. I want to prove two of the limit laws using the definition. So here's how it's going to work. So here's a claim. Um, if so, let's give these names actually. So we're gonna say if L defined to be the limit as x goes to a of f of x, and M defined to be the limit as x goes to a of g of x exist, then so we're assuming that these two limits exist, and we're going to call them L and M respectively. Then, if you take the limit as x goes to a of the sum, it's the same as taking the limit uh of the sum of the limits. The limit distributes, the limit operator distributes over the sum. So let's prove this. Oops. So proof. So we have two statements, okay? We have, so how does a proof how does a limit proof start? Well, it starts like this. Let epsilon be arbitrary. Okay, and then we want to find a delta such that if the following holds, if um x minus a less than is x minus a absolute value is less than delta, then the then f of x plus g of x, oops, minus L plus M, the limits less than is less than epsilon. That's what we want to prove. We want to prove that this sum approaches the sum of the limits, because L and M are the sum of the limits, right? L equals this one, M is equal to this one. So that's what we would need to prove in order to that's what we would need to show in order to prove the conclusion. So that is, if I give you an epsilon, you can find a delta such that when x is this close to a within the epsilon units, the sum of these two functions is within epsilon units of the sum of the limits L and M. The L and L plus M is the sum of the individual limits. Well, given epsilon, there exists now. So since we know these individual limits exist, right? If I give you an epsilon, there has to exist a delta one associated to this thing, and say a delta two associated to this one. So there exists delta one positive. Oh, that's notation you probably don't know. Backwards E just means exists. It's actually a lot more convenient to use it because who wants to write there exists every time? But I won't, just because you might not be familiar with it. So given this epsilon, there exists, I should say, delta one greater than zero and delta two greater than zero, such that the following two statements hold. We have like, no, it's not. Let's leave like bullet point one and then bullet point two. Um, if x minus a is less than delta, this implies that f of x minus L is less than epsilon. And two, x minus a less than delta 2 implies that g of x, so g of x minus m is less than epsilon. So we're kind of close. We want a delta, but we're given these two deltas. So maybe there's a way to like extract a single delta from these, and it turns out there is. It's actually oh, sorry, I don't want less than epsilon. I want to be less than epsilon over 2. Okay. So given any epsilon, I can find a delta 1 and a delta 2 that make 1 and 2 true. And if I give you any epsilon, then the definition for should also work for epsilon over 2 because epsilon over 2 is another positive number. So here's the trick. You want to like extract a single f delta. So you say this is what we're gonna do. We're gonna let delta be equal to the minimum of f delta 1 and delta 2. So if now what that means is then is that if delta x minus the distance from x to a is less than delta, then it's less than both delta 1 and delta 2. So this implies that these both hold simultaneously. So now we have this single delta that makes both of these ones work out. But if these work out, if these two statements are true, then because these are implications, this statement will be true and this statement will be true. And that's what we're going to use. So we're going to use that now. So we're going to compute. This is what we want to show. Going back to it, just to remind you, we want to show that if x minus a is smaller than delta, then the sum of the two functions is epsilon close to the sum of the limits. So we want to compute this right here and show that it's actually in fact less than epsilon. So let's do that. So we got the sum of the two functions minus the sum of the limits. And that's what we're gonna do is we're gonna put the f of x with the L. So we're gonna put the f of x with the L, so it's gonna be f of x minus L. And then we're gonna put the g of x with the m, so it's gonna be g of x, not plus m, but minus m. And now what we need to do is recall the triangle inequality. The triangle inequality says that if you say you do, I don't know, I guess a plus b, the absolute value of a plus b is less than the absolute value of a plus the absolute value of b. So this would be like your a right here, this would be your b right here. So this is going to be less than or equal to, I'm just going to apply the triangle inequality. So this whole absolute value right here would be less than or equal to the sum of these absolute values. But now, remember what we're assuming. We're assuming that x minus absolute value of x minus a is less than delta, and that implies that these two hold, and those two holding implies that these hold. And so we know that this thing right here is less than epsilon over 2. This thing right here is less than epsilon over 2. So it's less than epsilon over 2 plus less than epsilon over 2. And of course, when you add those two, you just get epsilon. So what we proved is that these two things, the absolute value of this right here is strictly less than epsilon. And this works for every epsilon. So if I give you any epsilon, you can construct the delta in the way that we did. So what this proves is then hence the limit as x goes to a. I should point out that this a is not the same as that a. I just use that as a variable for the sake of recalling the triangle inequality. So just don't get those two confused. So the limit as x goes to a of f of x plus g of x, we proved is the same thing as L plus m. But remember, L plus m is we define them to be the limit of x as x goes to a of f of x plus and then m was the limit as the limit as x goes to a of g of x. So we proved it. We proved that the limit can distribute over the sums. So it might seem like a lot of work. Yeah, there was a lot of work to go into proving this one law, but you can imagine that this one law has a ton of consequences now. We can prove a lot with them. And you can prove the other ones in a somewhat similar way. And I'll leave that to you. Maybe I'll make it a bonus or something. I'm not sure exactly. what I'll do. So that's that. And then one last thing I want to talk about, and then that'll be it for this video, is the so-called squeeze theorem. So this is a really important thing. Again, this you prove using the epsilon delta definition, but it has a lot of consequences. So let me see. So I'll just show you this and then show you the picture. So the squeeze theorem states that if you have that this inequality holds just near A, except possibly at A, that's how these limit laws are usually phrased, is that you don't need some property to hold at A, but just near A. So if you have that this inequality holds, so g of x is bounded between these two functions, f and h, and you know that f and h approach the same number as x goes to a, then this forces g to approach that same number as x goes to a. And here's just a visualization. So you have f is the curve g, sorry, the red curve is the function g, and you can see near a, maybe like on a pretty decent sized interval, maybe like for example, this interval right here, the function g is bound between h, the green curve, and f, the blue curve. Of course, over here it goes outside of, it's no longer bound, but we don't care about this part. We only care about the part of the function near a. And you can see that the function is literally, as the theorem indicates, being squeezed at this point, and where the value of the function that they're getting squeezed at is L. So that's an illustration. Maybe the next video I will prove that, but I think I've proved enough in this video. I maybe need a break. So I think there's an example. Maybe let's see. Okay, so you want to use the squeeze theorem to prove this limit right here. Do they have a picture of it and a drawing of it? Yeah, here's the function actually. This is the function y is equal to x sine 1 over x. And so you have these two parabolas, x squared and negative x squared, and the function sine of 1 over x is pinched between these two parabolas. So you can see from the picture that you're going to be able to apply the squeeze theorem. But how do you do that? Well, first of all, let's think about why we can't avoid the squeeze theorem. As it says, you cannot write the limit as a product of the limits, this one and this one, because this limit doesn't exist. Remember, this rule works. This limit law right here works where you split the limit over the product. Only if each individual limit exists. But this limit does not exist. I guess this is example 225. Let me see. Let's see, what does that one look like? I don't see an example 225. Oh, maybe it's examples. Oh, it's section 2.2, example 5, I guess. Where's example 2? Oh, right here. Oh, they're looking at sine of pi over x, but sine of 1 over x basically looks the same as that. And we saw because the function, when you take the limit as you go towards 0, it oscillates a bunch. So there's no limit. So that's why. And basically the same reason why this example, that's the same reason why this limit doesn't exist either, because it oscillates near x equals 0. So we can't just split up the limit and be done with it. We have to use the squeeze theorem, but here's how you do it. Remember that the sine function is always bound between 1 and -1, right? So in particular, sine of 1 over x is also bound between 1 and -1. And what you're going to do is you're just going to multiply each side of the inequality, this one right here, by x squared. So we have negative x squared and x squared, and then this is the function whose limit we're interested in right here. So we have this function is squeezed between negative x squared and x squared. Now we know that these limits individually, so the limit of x squared is x was zero is zero. We know that this one is zero also. So these two functions have the same limit and they squeeze or they pinch this function right here. So we can say by the squeeze theorem, we can conclude or obtain that this limit also equals zero because the limit is forced to equal the common number zero. This common number is zero. All right, that's all for now. So let me turn this off.